Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is Newton's third law, third and final law that we'll be looking at in this part of the course. The questions that we're going to answer today are going to help us to understand finally just how and why objects move the way they do in any situation that you can think of. So by the time you've finished watching this video and have understood Newton's third law, that together with the second law that you learned in the last video and the first law from the video before that should, in theory, give you the ability to explain what's happening when you watch the motion of any object. And if you think about it, that's a pretty powerful idea. The thought that there are just three rules which, while they can be tricky to apply, they're fairly simple. That there can be three simple rules that can explain any situation that you can encounter. That's the genius of Newton, that he explained motion in three simple rules. And today you're going to get the third of those rules. So take a moment in a second to pause the video and have a look at the questions we're going to address in this video, as well as where we are in the unit schedule and what are the learning goals and success criteria. Please do that now. Okay, and you're back. We're going to get started. Here we go. I'd like you to start by having a look at each of these 6 pictures. Actually, 5 pictures really. This one here, which is a screenshot of a YouTube video. We're going to actually go and watch this video in a moment. And don't worry, this guy is just doing target practice in an indoor range. He's not going to shoot anyone. So here's what I'd like you to do in a moment. In a moment, I'm going to ask you to pause the video once again. And I want you to go through each of these pictures and answer the following question. For each of the main objects that you can see, and what do I mean by main object? So here it would be one of the swimmers. Here it would be the runner. Here it would be the rocket ship. Here it would be, well, there's actually a few main objects. You could think of the guy. You could think of the gun that he's holding. You could think of the bullet that he's going to shoot. Here you could think of the person who's trying to rescue the person who's gone over the edge of the cliff. Either of them you could be thinking of. And here you can be thinking of the locomotive and the train cars that are behind it. So for each of those objects, in a moment, pause the video, and I'd like you to draw a free body diagram for each of them and see if you can identify what forces are acting. Okay, please do that now and then come back. Okay, and you're back, and now we're going to go through it. We're going to look at the free body diagrams that you've drawn against what I'm about to draw. So, for the divers who are clearly about to dive forward, I think we all know that there's got to be a force forward on each one of these. So I'm going to pick this guy in the middle here, or this woman actually, and I'm going to say that there's some sort of force pushing forward. What is that force? Well, we're going to find out in a moment. What we do know about the diving, everyone's done something like this before. You've all lurched forward in some way, whether it was into a pool or maybe on skis or on skates. You push backward. So there's some sort of backward push here. I'll draw that maybe in red so it's a little bit easier to see. There's a little bit of a backward push, but you're pushing against the starting blocks. You're not pushing against yourself. So the question I asked you before you paused the video was, can you draw the free body diagram of the person? So actually this diagram, this force vector here, we don't want that. That's a force vector exerted on the diving block, and we're talking about the diver. So I'm going to go back and just undo what I drew there to get rid of that. There is in fact only this forward force acting on the diver. Well, to be fair, there's also gravity downward, but I'm just trying to focus mainly on the forward motion, so forgive me if I leave out gravity just for now to keep things simple. There's really only a forward force acting on the diver. What about the runner here? Again, the runner is moving forward, and if he didn't run with his, exert force with his legs, he wouldn't go forward, so there's got to be something pushing forward. Sorry, I got to work on my straight lines there. There we go. There's something forward. However, did you also draw a backward push like this? If you did, you're right, there is some backward pushing, but what the runner pushes backward on is the ground. And I didn't ask you to draw the free body diagram for the ground. I asked you to draw the free body diagram for the runner. So forgive me if I'm going to leave that out. I'm going to delete it. Of course, there is also gravity down and the normal force up. However, since the important motion here is over to the right, I'm also going to leave those out. I just want to keep things simple right now and focus on this forward force. How about the rocket ship here? The rocket ship is clearly experiencing a force upward, We can see that by watching any rocket take off. There is gravity down, of course, and we can't ignore that. But for now, I want to keep things simple. The motion that is of importance here is the upward motion, so we really want to analyze this force here. We're not so concerned with the gravity. So please allow me to leave that out for a moment and just realize there's some sort of force upward. This video here, let's skip to that right now. It's a YouTube video, which I have queued up here. You can see where it's from, and I'm just going to mute it, and we're going to play, and you're going to watch what happens. Actually, before I hit play, can you predict what happens? If you've ever watched a gun being shot in the movies or on TV, I think you know what's going to happen. But let's watch the video just to see. So you can see he fires the bullet, and he goes backward, okay? But in this case, what did you draw your free body diagram for? Did you draw the free body diagram for the person? Then you should have drawn some force going backward. Or did you draw the free body diagram for the bullet? The bullet goes forward. The gun itself, which is attached to the person, also goes backward. So those are some of the possibilities for what you may have drawn here. What did you draw here? This is a little bit of a tricky situation. Usually when we see this in the movies, the person on top is saving the life of the person on the bottom, and so we understand that this person, if she's going to be saved, is experiencing a force upward. But although I've never been in this situation, thankfully, I can imagine it could go the other way. Maybe there would be a disaster. Maybe this person would pull this person, the rescuer, down. Maybe the rescuer would go down. So I don't know what would happen. I didn't see this movie, if it is in fact a movie, but you can imagine there could be different force vectors attached to different objects. What about the train here? It's pretty clear that the train is moving forward, so we can definitely draw a force forward. However, let me ask you a question. What do you think the motion would look like if we were to get rid of the cars behind the train, the locomotive? In other words, if it was only the locomotive, how would the motion be different if all this locomotive had to do was drive itself through the mountains here? Would it be an easier time that the locomotive would be having to make the trip? Absolutely. It's hard to pull all these cars that are behind it. So maybe we can say that while the locomotive is pulling itself forward using its engine, these cars are sort of making it harder. They're pulling backward on the locomotive. So now we've sort of done a very rough and inexact analysis of what's going on in these situations. So what I'm going to do now is go back through them, and I'm going to give you the technical analysis so that you can compare the sort of wishy-washy description I just gave with what a physicist would say. Here's what a physicist would say. A physicist would say that the swimmer here is exerting a force backward on the diving block. And so I'm going to write that in one more time as force of swimmer on the block, the diving block, Fs on B. Now, the swimmer goes forward, and you might think that the swimmer pushed herself forward, but she didn't. She was pushing backward. She was exerting the force of the swimmer on the block. What pushed her forward? Well, a physicist would say that it was the block that returned a force forward on the swimmer. So if B equals block and S equals swimmer, now you know what these letters stand for officially. We have two forces here, but on different objects. The only force on the swimmer is the sort of return force of the block on her. Now, in physics, in Newton's third law, what Newton's going to do for us in a moment is explain exactly how many newtons of force each of these vectors represent. So hold on to that thought for one moment. Let's go to the runner here. The runner is pushing backward on the ground, which really means earth. So I'm going to call this the force of the runner on earth. R equals runner. E equals earth. Or you could use the letter G for ground if you wanted. What is pushing the runner forward? It's not the runner. The runner's pushing backward. Look at his feet. Well, the only thing that could be pushing him forward is the Earth, the thing that he's touching. So a physicist would say that this is the force of the Earth on the runner. What's going on here? This one's a little bit trickier. A lot of people think that the rocket ship is pushing down on the ground, but I can prove to you that this is not really the case. If the rocket ship uses a force against the ground in order to lift up into space, then what would you imagine is its method of propulsion once it gets way up into the sky? Once the rocket ship is way, way up, thousands of feet in the air, is it still pushing on the ground? What about once it's in the upper atmosphere, 70, 80, 90,000 feet up? Is it still pushing on the ground? I think you can see the answer is no. The rocket ship, in fact, does not even need the ground to be there in order to lift off. What is it pushing on? Well, believe it or not, the rocket ship is basically built around an engine which pushes these hot gases down. This hot gas is composed of countless molecules that are moving very, very fast. What we've got here is a downward force, which is the force of the rocket on the gas. And so R equals rocket, G equals gas. In return, the upward force is the force of the gas on the rocket. Remember, it's not the ground that's pushing up. We know this because once spaceships get way up in the air, there's no ground anywhere near them to exert that force. Okay, back to the shooter here. Now here we have to define which object we're going to pay attention to. So what I'm going to focus on is the bullet. And just to make it easier to see, let's put a black dot as the bullet here so that we've got something to look at. What is pushing the bullet forward? Well, it's the gun. That's what guns do. They push bullets forward. So we have a force of the gun on the bullet. G equals gun. B equals bullet. Oops. There we go. What is pushing backward on the man? Well, it's the gun. So let's focus on the gun here. It's the force of the bullet pushing back on the gun. That's what a physicist would say. And of course, the gun is being held by the man, and so in the video you saw him go back when he pulled the trigger. What's going on here? To me, this kind of looks like a police officer, and this looks like a victim, someone who's about to go over the edge. So let's say P equals the police officer, V equals the victim who she is trying to save. So clearly the police officer is pulling the victim up. This is the force of the police officer on the victim. However, as I mentioned earlier, sometimes both of them go over the edge. Sometimes the police officer can't help but get pulled over the edge, and unfortunately they both fall down. This is the force of the victim pulling on the police officer. Now, does that mean that the victim would purposely pull the police officer down? No. Why would she do that? It would just cost her her life. However, we can imagine that maybe she's so heavy, or maybe the rocks are so slippery and loose that the police officer can't help but be pulled over. So this could actually happen. And finally, with the train here, we've got the locomotive. So L equals the locomotive. And the car behind it, that'll be the letter C. So what are the forces here? Well, first of all, the forward force on the locomotive, let's see how this happens. The locomotive actually spins wheels which push backward on the ground, much like the runner pushes backward on the ground or earth. Now that's a little complicated, so I'm going to call this the force of the locomotive just pulling forward. However, the locomotive is pulling on the cars, so what ends up happening, because there's all those extra cars there, it makes it harder for the locomotive to go forward. Remember, it's easier for the locomotive to move if there are no other cars. So something is holding it back. That is the force of the cars on the locomotive. And of course, the locomotive is exerting a force on the cars. So here again, we have forces pulling in different directions. Now, to get a little bit more specific here, I know I haven't really treated this one exactly the way I've treated the others. Each of these other ones have 2 letters for each of the forces you can see in every situation. But here I kind of left one out. We're going to do a problem like this in a couple of screens, so bear with me on this one. I know you're probably thinking, this one's a little trickier. We will get to train type problems shortly. But my point is this. For every force that someone chooses to exert, swimmer on the diving block, runner on the earth, spaceship on a rocket on gases, and so on, there is a force going the other way acting on the original object. So here the blocks return a force on the swimmer. The earth returns a force on the runner. The gases return a force on the rocket, and so on. Here's what Newton's third law, or rule, tells us. It tells us that these forces have equal magnitude, so the same number of newtons, but of course, as we have seen, they have opposite direction. And so quite often you'll hear people call Newton's third law the law of action and reaction, which is to say that for every action force there is an equal and opposite reaction force on a different object. You can't push the ground without getting pushed. You can't fire a bullet without getting pushed backward, and so on and so forth. Sometimes you can't pull someone up without yourself getting pulled down. All right, let's look at a simple example here. Here's a picture I found on YouTube. I have no idea who these kids are, but if you Google image search for something about people sitting on skateboards pushing each other, you will get to a physics page which has a very classic demo. 2 kids sitting on roller skates, and the assignment from their teacher is the following. I want one of you to push on the other. So maybe this kid over here pushes like that on his friend. And the friend over here is instructed not to push, just to hold his hand steady. And the idea is, if this is the only guy doing the pushing, what's going to happen? Well, certainly the friend is going to go backward. We know that that's going to happen. It's very clear that this guy's going to go backward. He's on wheels. But will this guy also go backwards in his direction, this way? Well, try this. If you have a chair on wheels at home, go up with a friend, put 2 chairs on wheels together, and try one of you pushing and the other one not pushing. See if you can make it so that just one of you moves. Guess what? You're not going to be able to do it. It's because of Newton's third law, the law of action and reaction, that says when boy number 1 pushes boy number 2 to the right, boy number 2 will return a force on boy number 1 to the left. So let's look at a numerical problem and see if we can solve it. The boy on the left, boy number 1, 22 kilograms. So he's over here. Number 1 is going to push the boy on the right, boy number 2, who has mass 29 kilograms, with a force of 35 newtons to the right. Determine each boy's acceleration. So here's what we're going to do. We're going to draw a free body diagram for each of these boys and try to use it to solve for the acceleration. Now, this is boy number 1, so we'll call him M1. And this is boy number 2, we'll call him M2. Now let's see what's happening. Boy number 1 is pushing on number 2 to the right. So here's a force to the right, and I'm going to call that the force of 1 on 2. Of course, Newton's third law tells us that if number 1 pushes number 2 to the right, then 2 will push number 1 to the left. That's the equal and opposite part. So this is force 2 returning a force on 1. And we know that these are equal in magnitude according to Newton's third law, so I give them each a tick mark. Now, of course, there is gravity and some sort of normal force acting on both of these boys. However, as long as we see that they are not accelerating up or down, we know that those are equal. So I'm not going to leave them out this time. I'm going to try to be as careful as I can to encourage you to do the same. Tick, 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 tick. Those are equal. What other forces are there? Well, there's probably a little bit of friction, but I'm going to neglect friction for now just to keep things simple. I should have written that into the problem here. So what do we know about the magnitudes of these forces? Well, I've said that force 1 on 2 is going to be 35 newtons right, so I can put that in here, 35 newtons. But according to Newton's third law, which we wrote up here, equal in magnitude, we also know that the return force will be 35 newtons to the left. Now what do we do? Well, when you want acceleration and you're dealing with forces, you use F net equals ma. You use Newton's second law. So in order to do that, you need a free body diagram, which we do have. A equals F net over m. And so now we can write 35 newtons to the left plus the gravity force, which normally I would write mg and I would calculate it, but I know that they're going to cancel here. So I'm going to write them in anyway. Yeah, I'm going to cross them out right away. However, it's important to realize that these forces do exist, and you should therefore include them. Let me give us a little bit more space here. There we go. Okay. Whoops. And we're going to write in the mass of this boy, which is 22 kilos. So what do you get? 35 over 22, it's going to be around 1.5, give or take. So let's see, 35 divided by 22, I get 1.59, or roughly 1.6 meters per second squared. And if I do the same for the other boy, just to save time, I'm not going to write everything out. I'm going to leave it to you to see that the force is the same, 34 newtons this time to the right, 35 newtons to the right, but this time distributed over 29 kilograms, which will give me a lesser number, 35 divided by 29 I'm doing. I get 1.2 meters per second squared. And of course, I should include the directions to the right and for this one to the left. Now, look at what this all means. Let's put things back there. What does this mean? It means the lighter boy gets a greater acceleration. The heavier boy gets a lesser acceleration. That is what's different here. It's the force that's the same according to Newton's third law. And remember, these are acting on different objects, so I hope you don't think the forces cancel out. One of the common mistakes students make is they say, well, 35 newtons left cancels 35 newtons right. That would be true if they were acting on the same object, but they're not. They're acting on different objects, and this is extremely important. It's why we draw our free body diagrams, and we're very careful with symbols to do the correct labeling. All right, moving on. Here's a question that's right out of your book. The book is Physics 11 by Addison Wesley, and so let's have a look. This is what I call a train type problem, and remember when I told you a little while back that I was not quite using the same letters the way I did with these kind of questions? Like, all I wrote here was FL, and here I put, there's only one letter here, but all of these had 2 letters each time. Well, now we're going to do a train type problem, and you'll sort of get an idea of what I was talking about. Here you see there are 2 blocks, X and Y, attached by a string, one of them being pulled by some force. Let's read the question. 2 steel blocks at rest on a frictionless horizontal surface, block X mass 6 kilograms, block Y mass 12 kilograms. A force of 36 newtons is applied to block X. Now they don't tell you where this force comes from. It could be somebody pulling with a string that's attached to X. This force is analogous to the force here that the locomotive exerts. Remember, how does a locomotive work? It's got a diesel engine which turns the wheels. The wheels push on the ground just like a runner's legs push on the ground or feet push on the ground. In return, the ground pushes the runner forward. In return here, the ground pushes the locomotive forward. Now I didn't want to get into locomotive, ground, and cars here, so I kind of fudged it a little bit, but now we're going to see how this all works out. There is some force pulling to the right here. They don't tell us where it's from. We'll deal with it. Now, there's this block attached here, and it says, let's see what they say, calculate the force block Y exerts on block X. In other words, it's kind of like saying back here, what is the force that all these other cars behind exert to pull back on the locomotive? Because if you think about it, the locomotive would make it along its trip much more easily if it didn't have to pull all these cars. It's almost like these cars are holding it back by exerting a force. That's what we're looking at here. So what do? Same thing we did previously. We draw a free body diagram. So let's have a look. Here's the free body diagram for block X. It is being pulled forward by some force that we are not told where it comes from, just that it is 36 newtons to the right. What other forces are acting? Certainly there is a normal force, and certainly there is gravity, and as long as we're sitting on a horizontal surface without accelerating up or down, these forces are known to be equal. All right. Are there any other forces acting? Well, yes. There's that backward force, which is kind of like with the train cars that I talked about earlier, that's holding it back. But what force is that? Well, we'll leave it as a question mark for now. I will just point out to you, there is a string here, and in a string, we often have tension forces. So I will eventually write F tension, but before I do it, let's look at this block here. Because I think if you look at this block, things will get a little bit clearer. This is block Y. What forces are being exerted? Certainly gravity, certainly a normal force. And again, as long as block Y is not flying up in the air or sinking down into the ground, those are equal. But is that all? The answer is no. If somebody pulls on block X, and block X is attached to block Y, that string is going to pull block Y in the forward direction. Without that tension force, block Y won't go anywhere, which is kind of like saying these cars won't go anywhere unless the locomotive pulls them. All right, so we know there's a force forward, and it wouldn't be a bad idea to call this the force of X pulling on Y. After all, this is like the locomotive pulling on Y. But now we're going to solve our mystery here of what is this question mark force. Well, here's what this question mark force is. If we know that X is pulling Y forward, what does Newton's third law tell us? It tells us that Y has to simultaneously pull X backwards. And therefore, this force, 3 tick marks, is equal to this force, 3 tick marks, because of Newton's third law, which tells us that these forces are equal and opposite. In other words, the force of X on Y is equal to the force of Y on X, except in the opposite direction, so a negative sign. This is very important. We're going to come back to this formula very shortly, so don't forget it. Very important. I'll highlight it in red so you don't forget. Now, let's look at how we solve this. We can now apply Newton's second law like we did with the two boys on the skateboard. If we've got a good free body diagram, we're going to be fine. A equals F net over M. And we're going to do this for block Y. What have we got? The net force. Normal and gravity cancel, so I'll write Fn, I'll write Fg, and I'm going to cancel them in a second. We've got the force of X on Y. We divide by the mass of Y, which I believe is given as 12 kilograms, right? And like I promised, we're going to cancel those. Okay, so what do we get down to? A equals Fx on Y divided by 12. Problem: 2 variables, 1 equation. We're not able to solve. However, if we go and write Newton's second law for block X, look what we get. Let's look at our free body diagram here. We can write A equals, now the normal and gravity cancel, so I'm going to write them, but then I'll cancel them. We have 36 newtons to the right, and get a little bit of room here. We've also got another force here, Fy on X. And we've got to divide that by the mass, which is 6 kilograms. Cancel the normal and gravity like I promised. Now, what have we got here? Let's just write this a little bit clearer. We've got Fy on X. Actually, I should write that as in the same order just to keep things clear. 36 newtons to the right plus Fy on X. divided by 6. Now, let's have a look at exactly what's going on here. How many variables have we got? Like I said earlier, we have acceleration, and we have, I'll use another color to show that we have fx on y. Here we have fy on x. Is that a new variable? It is. However, look what we know from here. We know that fy on x is the negative of fx on y. So I can actually replace this by using negative fx on y. That can be subbed in there. And this is just the same variable as that. So we don't really have a new variable here. What else have we got? We've got acceleration, and we had acceleration there. Now, if you think about it, when a train is moving, all the objects accelerate at the same rate. Think back to this diagram or this picture here. All the cars and the locomotive accelerate at the same rate. Same thing's happening here. So actually, this acceleration is the same as this. We really have two variables here, and we have two equations. So guess what? Just like in grade 10 math, where you solved two equations with two unknowns, that's what you're going to do here. Think of this as a simple variable. Think of this like a equals, let's call it f over 12. And think of this as a equals 36. Now you're going to put in a minus here, minus f over 6. And now use either substitution or elimination or whatever method you want to solve. Since both of these are equal, what are we going to get? We're going to get f over 12 equals 36 minus f over 6. And you can cross multiply or solve it however you want. What's that going to give us? 6f equals 12 times 36, I believe, is 480. I'm not using my calculator. I'm just hoping I'm right there to save time. Will it be? I'll just check just to be sure. Bear with me for 10 seconds here. 36 times 12, am I right? Nope, 432. Good thing I checked. Minus 12f. And what do I get when I solve that? Let me get a little bit more space here. I get, bring the 12 f's across, so I get this, 432. F equals 432 divided by 18. I get 24 as my answer. Now, remember, f was what I called this in here, just to keep things simple. So that's telling me that F is 24. Now forces are measured in newtons, and forces are vectors. What is the direction? The direction is the same as what we used here, so that'll be to the right. So this was Fx on y. Now let me look back at my diagram. Was x on y pulling to the right? Well, let's see. Yes, it was. Here's Fx on y. And as you see, it is pulling to the right. It also means that Fy on x will be 24 newtons to the left. And so now we can see a couple of things, and this is where I'm going to finish off. We have 24 newtons here, spread over a mass of 12 kilograms. What's the acceleration? Well, sub into here and solve for the acceleration. 12 newtons to the right, divided by 12 kilograms. What's that? Sorry, 24 newtons to the right over 12 kilograms gives you 2 meters per second squared. We should get the same acceleration if we use this formula here. Let's see what we get. A equals 36 newtons right. Now remember, this was Fy on x, that's 24 newtons left, so plus 24 newtons left over the 6 kilograms. Now what have we got here? 36 right, 24 left. That leaves you with 12 newtons to the right, divided by 6 kilograms. That is also 2 meters per second squared right. Did we get the same accelerations? Yes, which we should. And that's a way of verifying that you haven't made a mistake. So there you have it, folks. That's how to solve a train type problem. They are a little tricky. You really have to use good symbols here. Keep your symbols straight. Otherwise, you're going to run into trouble. And of course, don't forget Newton's third law up here, which is the key to solving. And it allows you to use two equations with two unknowns. All right, and that's about it. And by the way, the fact of the video is Newton's third law, the law of action and reaction. The idea that when forces act, they act in pairs that are equal in magnitude but opposite in direction, and we should point out they are on different objects. One neat way that I've heard this law be described is you can't push without being pushed. You can't push something and not be pushed by yourself. In other words, not get pushed by yourself. In other words, you don't exist in your own little world. Everything you do that influences something outside of you comes back to you in some sort of way. All right, and I will leave you with that. Have a good day, and I'll see you in class. Thanks for watching.